right now let me roll on. There are interesting games you play in the heuristics to help with that kind of stuff. So it's not so bad. So new topic, it's the Amdahl's law. As most VM implementers already know, Java locks tend to come in a couple different varieties. There's the ones that never ever see contention ever, and those are already well served by bacon bits or some other thin lock form. There's the locks which you actually do block on, and you just have to have OS support. You have to do some sort of sleep and wake up. And then there are all these locks in the JDK which guard against a very rare concurrent writer, but most of the time there's no real contention. In the 99% cases, you took the lock, but the only other person competing for the lock was another reader. So we have hardware support for speculative locking, somewhat similar in spirit to the SLE paper or transactional memory. It basically, it works much the same way. You turn on speculation mode, you begin marking lines in your cache as being a speculative state, and you don't let the writes escape your cache. They're just marked speculative if you're writing, and otherwise speculative shared if you're reading. And at the end, you're either going to abort or commit, and if you commit, then you atomically make all those writes visible to the rest of the system, and you put the speculation bits out, and you win. And if you have to lose a line out of your cache, you have to give a line up, then you lose. You now mark all the writes invalid, so you don't ever export those writes. No one ever saw it happen. And you roll back your state, and software decides to retry or go to a heavy lock. Kind of. Software has to decide whether to roll, retry, or go to a heavy lock.
On what granularity do you do this?
I'm sorry?
On what granularity do you do this?
Cache lines. Cache lines that fit within your L1.
One cache?
No. As many cache lines as fit in your L1. So it's lots of different cache lines. But there are limits. If your cache lines, however many way associativity, if you touch too many lines of the wrong pattern, you might never make progress. And so eventually the software has to decide this is a waste of time, go to a heavy lock. So these are sort of odds and ends. So most objects have, in an object-oriented system, the objects have a type stored in the header somewhere. The object type class, whatever you want to call it, is commonly loaded for virtual calls and subtype checks. And we're implementing a 64-bit VM. So we have these big pointers, 64-bit pointers. They refer to an address space which is much, much larger than sort of useful memory floating around. So we're going to jam into the pointer itself a pile of bits that describe the object's class. We call this a class ID. And we can get at it without doing the load. We just extract some bits out of the pointer. And then we can remove the pointer from the object header. And we still need these class ID bits, but they're a lot smaller than a full-blown pointer. And you need a few other bits, but we believe we can get down to having a 4-byte header and a 64-byte VM. That's not implemented, but I don't see any reason why it can't work.
How does that help you overloading the store? Well, I guess you can get the header size down, but you still need to you then need to do a load from a table to get to the method.
It's gone. So here's a typical type equivalence test. So we're going to do an extract and pull the class ID bits out. We're going to compare it against an immediate value, which is a small thing that's no bigger than a class ID and branch. And I avoided the load. So this gives me you are equal to or not equal to a particular class without doing the load. I never had to look at the header bits at all. And that's the same pattern that I typically use for predicted virtual call. A predicted virtual call is one where I ask, is the receiver of the call this pointer of a particular class? If it is, I take a static jump to the target. And I'm going to do that in one instruction. I'm going to, this thing we call comp class, it's going to compare the kid bits in the pointer against what I hope is the right answer, and trap or do nothing. And then the next instruction is a subroutine call to static subroutine call to the expected target. And so now I don't have to do a dependent load here at all. I don't have to actually load in the header bits into my cache even because I don't care for them. And this is one of the most common uses of class ID bits, of the class pointer.
what percentage of the time do you have to do this versus and out those bits when you really want to use the pointer?
The hardware ends them out.
Oh, okay.
Cut those wires off.
I just said part that you had hardware
Cut
support.
those wires off.
Okay, so
So I mean, I'm assuming if you actually read data from the object, though, you're gonna. So how much do you really win?
Yeah, so it's a fractional improvement game. Some fraction of the time, the header bits are no longer pulled into your cache.
Okay, that's fair.
But you still, when you say the header bits, you still need the KID.
The
Right.
KID field in the pointer I have already in a register.
Oh, I see, the pointers to the things are tagged. Got it. Okay.
Okay, so we go on. Let's look at a megamorphic or an unpredicted virtual call, which is typically load class out of the object header, load something out of a vtable index. So these are two dependent loads, and then you jump to the target you get. That's, I guess, a good common way to do an unpredicted vcall. And so I can now play this game you were talking about. I can clone portions of the vtable into some sort of fixed size table and do, shift and add. So get the KID out with an extract, shift and add against the table base, and do a load to get the vtable index out and jump. So I end up with one load and a jump register. And then I can go one better and I can jam the actual target address as a jump instruction in the table. And now I can do a megamorphic virtual call with no loads. Well, no decache loads. There's an iCache.
But an extra jump.
There's an iCache load. It's a statically predicted jump. This one is hard, this jump register, but this one's the hardware's going to fetch that and jump to it. So it is a trade-off between whether it's faster to take
a. You can predict it. It's unconditional, but you don't know where you're going until you fetched it.
It's going to depend on your exact hardware implementation, whether a load, which you have to wait till it appears in a register and then do a jump register and restart your pipe, or start your pipe early and then take the hiccup for the jump, which is too far ahead to know where it goes. Minor things, and I got to quit real quick because I'm going to get kicked off. We're range check opt. Uncontended CAS instructions are really cheap. Java compliant subset of IEEE. Safe point pulling in hardware, so you get some VM OS cooperative preemption game going on there. What else? This has been a lot of fun. The chief CPU designer sits right next door to me, and so we shout over the cute wall at each other about what I can and can't get in the hardware and what he can and can't do in software and all that kind of stuff. So comp class and bits and pointers were sort of cooperative. Neither one of us like dividing 0 causing a trap, so it doesn't. Headache for me. Shift and add has this particular flavor in 64-bit Java land. You need a sign extender 32 bits, and then do a 64-bit shift and a 64-bit add to do array addressing, or you get wraparound at very large indice issues. So we have tons of cool hacks in the hardware that
Yeah, putting all these PLDR tapes.
I don't have time. So what can I say here? It's real. We have this stuff. It's running. I sort of feel like this is the first real GC hardware that's been out in a long, long time. It's a very serious hardware software co-design. We have a very large, for a startup, hardware team, fairly large software team. We've been talking to each other deeply for quite a while now, and it's looking really cool. My lawyer meeting secrets. Sun, microsystems, Java, done. Okay. And what can I answer within the limits of what I can answer?
So, yeah. Well, I'm not sure how much you can answer, but let's say you go to a customer, he's got box with today's hardware technology and the VMs you've heard about that are available today, and then he gets to use your box. Without getting into the real internals of what percentage of difference of cache misses and all, what's the bottom line benefit that he'll see? Is it performance, isolation, usability, reliability? I mean, what will really change his life or her life?
This plays straight into the sort of the business model of why,
Right.
And it's something I cannot say. So I can answer sort of technical bits about the hardware things that drive into the business model. I'm going
Okay,
to